Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1919 marks a watershed moment in the annals of nuclear physics. Ernest Rutherford, already a titan for his scattering experiments and planetary model of the atom, published Artificial Disintegration of the Elements, a paper demonstrating, for the first time, the transmutation of one element into another under human agency. This essay provides a thorough evaluation of the claims contained within that seminal work, examining its arguments, methodology, and evidentiary basis, with particular emphasis on the internal coherence of its structure and the intellectual landscape it both reflected and reshaped. We will proceed systematically, section by section, to dissect Rutherford's reasoning and assess the validity of his conclusions. Section 1: Introduction and Initial Observations. Rutherford's initial pronouncements frame the paper's central ambition to explore the possibility of disintegrating atomic nuclei through collision with alpha particles. He acknowledges previous work involving the passage of alpha particles through gases, specifically noting observations of long-range, swiftly moving particles emanating from hydrogen. Rutherford posits an explanation for these particles as liberated hydrogen nuclei, or protons, released from the disintegration of nitrogen atoms within the air. The claim is bold, suggesting the nucleus is not immutable, but susceptible to alteration. A critical examination of this initial hypothesis reveals a careful extension of existing knowledge. Rutherford leverages his prior research on alpha particle scattering and the properties of radioactive decay products to construct a plausible framework. However, the crucial element of the claim lies in the assertion that nitrogen, previously considered stable, undergoes a change. This assertion requires meticulous evidentiary support. Section 2: Experimental Apparatus and Procedure. The heart of Rutherford's argument rests on the design and execution of his experiments. He details the apparatus with precision: a metal box containing a radioactive source of alpha particles, a screen coated with zinc sulfide for detecting scintillations light flashes produced by particle impacts, and adjustable absorbing screens for controlling the range of incident particles. Hydrogen absorption within the apparatus is meticulously accounted for by evacuation and, in some variations, replacement with carbon dioxide. Rutherford claims that these experimental controls, though seemingly rudimentary by contemporary standards, were designed to isolate and quantify the emissions produced specifically from the bombardment of nitrogen gas. We can assess the strength of Rutherford's case by considering the potential for confounding factors. The sensitivity of the scintillation method, which relies on human observation, introduces a degree of subjectivity. However, Rutherford addresses this by employing multiple observers and recording data over extended periods. The purity of the gases used, while not explicitly quantified in modern terms, is addressed through rigorous evacuation procedures and comparative experiments with different gas. Section 3: Scintillations in nitrogen and oxygen. Rutherford meticulously details the results obtained when alpha particles were passed through nitrogen and oxygen. He reports a significantly greater number of scintillations observed at longer ranges in nitrogen compared to oxygen. After accounting for the stopping power of the gases, he attributes these long-range scintillations specifically to hydrogen nuclei produced by the artificial disintegration of nitrogen. This is a crucial link in his chain of reasoning. He carefully eliminates alternative explanations, such as contamination from hydrogen gas, by demonstrating that the number of scintillations increases proportionally with the nitrogen gas pressure. This proportional relationship provides strong evidence that the scintillations originate from within the nitrogen itself, lending credibility to his claim of disintegration. However, it is imperative to acknowledge the limitations of scintillation counting. Accurately differentiating particles of varying energies based solely on the brightness of the light flash is challenging. Rutherford understands this, noting his reliance on range measurements to deduce the nature of the emitted particles. Section 4 Scintillations in other gases and solid materials. Rutherford extends his investigation to other gases, including argon and carbon dioxide, reporting a limited production of scintillations corresponding to hydrogen nuclei. Further, he strategically examines solid materials, such as paraffin wax and aluminum foil, which are known to contain hydrogen. He asserts that the number of observed scintillations produced from disintegrating these materials were far in excess to the number observed via the disintegration of nitrogen. His careful inclusion of these control experiments is paramount to bolstering the argument. The comparative data reinforces the case that the nitrogen disintegration represents a distinctive phenomenon rather than a common occurrence. Moreover, the experiments on hydrogen-containing materials serve as a comparative benchmark to establish the expected magnitude of hydrogen nucleus production under alpha particle bombardment. This calibrated approach, with its careful inclusion of controls and comparisons, strengthens the overall scientific rigor of the inquiry. Section 5 Nature of the emitted particles. Rutherford dedicates a section to characterizing the nature of the emitted particles, arguing that they are indeed hydrogen nuclei, equivalent to what we now term protons. He supports this assertion based on their range in air, which he compares to the range of alpha particles and beta particles. Additionally, he notes their deflection in magnetic fields, although this measurement remains qualitative due to the constraints of his experimental setup. He concludes that the Charga-Thomas ratio of the emitted particles is consistent with that of hydrogen nuclei. The analysis presented here exhibits an inherent reliance on indirect measurements. Rutherford acknowledges the limitations of not directly isolating and analyzing the particles, but underscores that the totality of evidence, encompassing range, scintillation characteristics, and deflection properties, consistently point to their identification as hydrogen nuclei. The scientific validity hinges on the coherence of this cumulative evidence, where independent lines of inquiry converge to support a singular conclusion. Section 6 Mechanism of artificial disintegration. Rutherford proposes a conceptual mechanism for the artificial disintegration process. He postulates that an alpha particle penetrates the nitrogen nucleus, resulting in the ejection of a hydrogen nucleus and, ultimately, the formation of a new, heavier nucleus. He suggests, though tentatively, that the new nucleus is an isotope of oxygen, possessing an atomic weight of 17. It is in this speculative framework that a certain level of intellectual humility becomes evident. He concedes that the precise nuclear transformation is not fully understood and that further experimentation is required to delineate the details, while providing the first explicit expression of a nuclear reaction involving both input and output products. The careful articulation of uncertainty is a hallmark of scientific rigor, indicating a clear distinction between empirical observation and hypothetical interpretation. The proposed mechanism, while ultimately incomplete in its details, provides a valuable foundation for subsequent investigations into nuclear structure and reactions. Section 7 Discussion and Interpretation. Rutherford delves into the broader implications of his findings. He emphasizes the potential of artificial disintegration as a tool for probing the structure of the atomic nucleus and exploring the fundamental building blocks of matter. He acknowledges the potential for disagreement and calls for more research. He notes the significance of the discovery for understanding the origins of the elements. As a debated topic, Rutherford's vision extends beyond the immediate experimental results. His interpretation projects a future where controlled nuclear transformations become increasingly sophisticated, unlocking new insights into the nature of matter and energy. This perspective reveals a deep-seated optimism about the potential of experimental physics to reshape our understanding of the universe. Section 8 Further Experiments and Refinements. Subsequent paragraphs elaborate on the importance of furthering the experiments with refined techniques. The paper concludes with an urging for the next generation of scientists to push the capabilities of the current equipment, he makes a call for using magnetic fields and other methods to better determine the nature of the emergent particles. This call to action serves as both a summary and a forecast. It encapsulates the accomplishments of his work while simultaneously setting an agenda for future research. Rutherford understands that scientific progress is an iterative process, where each discovery lays the groundwork for subsequent inquiries. Section 9, Contemporary Reception and Critiques. Rutherford's work was met with both excitement and skepticism. While the experimental evidence was generally accepted, the details of the disintegration process and the identity of the resulting nuclei were subject to debate. Some contemporary physicists questioned the accuracy of scintillation counting and the possibility of alternative explanations for the observed long-range particles. However, the experiments of Patrick Blackett, which employed cloud chamber technology to visually track the paths of alpha particles and disintegration products, provided strong confirmation of Rutherford's findings. Blackett's work, using sophisticated photographic recording, directly observed the transmutation of nitrogen into an isotope of oxygen, solidifying Rutherford's claims. Critiques and revisions, largely focused on the precise nature of the nuclear reactions, ultimately served to strengthen the overall understanding of artificial disintegration. They also served to highlight the significance of the work. Section 10. Lasting Impact and Legacy. Rutherford's 1919 paper stands as a cornerstone of nuclear physics. It demonstrated, for the very first time, that atomic nuclei are not immutable, and that one element can be transformed into another through other means. This discovery paved the way for the development of nuclear accelerators, the identification of new elements, and the exploration of nuclear forces. The implications for both scientific inquiry and technological advancement were profound and far-reaching. It is in this transformative impact that the true value of Rutherford's work resides. He not only unveiled a new phenomenon, but also established a paradigm for subsequent research in nuclear physics. He gave future scientists ways to test and refine the nuclear theory he proposed. Section 11, Methodological Considerations. A significant aspect of Rutherford's achievement lies in his methodical approach to experimentation. He carefully designed the apparatus, implemented controlled variations, and meticulously accounted for potential sources of error. His reliance on multiple observers and quantitative measurements, wherever possible, contributed to the robustness of his conclusions. However, it is vital to acknowledge that the experimental techniques available to Rutherford in 1919 were, by contemporary standards, limited. The scintillation method, subjective and tedious, represented a significant constraint, yet Rutherford overcame this limitation through careful statistical analysis and cross-validation with independent measurements. His scientific acumen lay in his ability to extract maximal information from the available tools and to interpret the data with judicious caution. Section 12, Conceptual Framework. Rutherford's work was deeply rooted in the existing conceptual framework of atomic physics. His previous research on alpha particle scattering and the planetary model of the atom provided a solid foundation for understanding the interactions between alpha particles and atomic nuclei. However, he also challenged conventional wisdom by proposing that the nucleus, previously considered a fundamental and immutable entity, could be altered through external intervention. While not explicitly articulated in the paper, his understanding of radioactive decay processes in which elements spontaneously transmute into other elements likely influenced his belief in the possibility of artificial disintegration. This blend of established knowledge and innovative thinking represents a defining characteristic of scientific progress. By building upon the achievements of his predecessors and daring to challenge prevailing assumptions, Rutherford was able to make a groundbreaking discovery. Section 13, The Role of Instruments. The instruments employed by Rutherford, while rudimentary by modern standards, played a crucial role in enabling his discovery. The metal box, alpha particle source, zinc sulfide screen, and absorbing screens constituted a system that allowed for the controlled bombardment of gases and the detection of emitted particles. The scintillation method, with its inherent limitations, demanded meticulous observation and careful interpretation. Rutherford's expertise lay not only in the design of the apparatus, but also in his ability to extract meaningful information from the faint flashes of light. This highlights the importance of the scientist's skill and ingenuity in translating experimental observations into scientific insights. It serves as a reminder that groundbreaking discoveries can be made even with relatively simple tools, provided that the experimenter possesses the necessary expertise and intellectual rigor. Section 14. Internal consistency of arguments. The strength of Rutherford's paper lies in the internal consistency of its arguments. He carefully builds his case through a series of interconnected observations and deductions. The experimental data, while limited in scope, consistently supports his central claim that nitrogen nuclei can be disintegrated by alpha particle bombardment, resulting in the emission of hydrogen nuclei. He addresses potential alternative explanations, such as contamination, through controlled experiments and comparative analysis. The proposed mechanism, while tentative, aligns with the observed phenomena and provides a plausible framework for understanding the disintegration process. This adherence to logical reasoning and evidentiary support lends credibility to Rutherford's conclusions. While some details remained open to debate, the overall coherence of his arguments laid a solid foundation for subsequent research. Section 15. Intellectual context of the time. Understanding the intellectual climate of the early 20th century is essential for appreciating the significance of Rutherford's work. The discovery of radioactivity by Becquerel, the identification of radioactive elements by the Curries, and Rutherford's own work on alpha particle scattering had revolutionized atomic physics. The understanding of the atom as a complex structure rather than a simple indivisible particle was rapidly evolving. Rutherford's discovery of artificial disintegration represented a natural extension of this emerging understanding. Furthermore, the development of quantum mechanics, while still in its early stages, provided a theoretical framework for understanding the behavior of atomic nuclei. Rutherford's work, situated at the intersection of experimental observation and theoretical development, played a crucial role in shaping the field of nuclear physics. Section 16. Addressing potential limitations. A comprehensive evaluation requires acknowledging potential limitations in Rutherford's work. The scintillation method, inherently subjective, introduced a degree of uncertainty. The purity of the gases used, while addressed through rigorous evacuation procedures, was not quantified in modern terms. The precise nature of the nuclear transformation, beyond the ejection of a hydrogen nucleus, remained unknown. While these limitations are undeniable, it is important to recognize that they were largely imposed by the technological constraints of the time. Rutherford's achievement lies in his ability to overcome these limitations through careful experimental design, meticulous observation, and judicious interpretation. He extracted maximal information from the available tools and presented his findings with appropriate caution. His pioneering work paved the way for the development of more sophisticated experimental techniques and a more comprehensive understanding of nuclear phenomena. Section 17. Implications for nuclear chemistry. Rutherford's discovery holds profound implications for the field of nuclear chemistry. His demonstration of artificial disintegration challenged the long-held belief that elements are immutable. He showed that nuclear reactions, resulting in the transmutation of elements, can be induced through external interventions. This opened new avenues for exploring the fundamental constituents of matter and for synthesizing new elements. The field of nuclear chemistry traces its ancestry back to Rutherford's insights. It is, in a sense, the offspring of those first experiments in nitrogen transmutation during the early 20th century. Section 18. The discovery's impact on transmutation. The transmutation of elements. Once the domain of alchemy was brought into the realm of scientific investigation by Rutherford's work, he demonstrated that the age-old dream of transforming one element into another was indeed achievable, albeit through nuclear rather than chemical means. His discovery not only revolutionized atomic physics but also captured the public imagination, inspiring visions of a future where elements could be synthesized at will, while the practical applications of transmutation have proven to be more complex than initially envisioned. Rutherford's work laid the foundation for future advancements in nuclear energy and nuclear medicine. Section 19. The philosophical dimensions. Rutherford's work raises fundamental philosophical questions about the nature of matter and the limits of human knowledge. His demonstration that atomic nuclei can be altered through external intervention challenged the deterministic view of the universe and highlighted the role of human agency in shaping the natural world. His discovery also underscored the importance of skepticism and critical thinking in scientific inquiry by questioning prevailing assumptions and challenging established dogmas. Rutherford paved the way for new understandings of the universe and its constituent elements. Section 20. The enduring legacy. The enduring legacy of Rutherford's 1919 paper lies in its transformative impact on the field of nuclear physics. In establishing the basis for nuclear transmutation, its scientific influence is undeniable. It demonstrated the mutability of matter and set the stage for the development of nuclear technologies. Rutherford's work serves as a reminder of the power of scientific inquiry to unravel the mysteries of the universe and to reshape our understanding of the world around us. His careful methodology and rigorous analysis stand as a model for future generations of scientists.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.